So far we have been looking at several downstream where you are trying to separate solids from slurry, extraction or recovery of the desired product, then we go into the purification of the product. Now we are approaching the end of the downstream where you are trying to dry the material, and generally drying is resorted to if your product is a solid. Why do you need to do drying? There are many reasons why you need to do drying, because when you do drying the product stability may increase, the quantity or the volume occupied by the product comes down, so it is much easier for you to transport. If there is moisture present, you may have bacterial growth, so it may contaminate your product, or sometimes the moisture present can lead to hydrolysis of the desired product. So because of all these reasons we need to go into drying. Drying is also a very important unit operation because it gives you a certain appeal to your final product which is accepted by your customer. So this is almost the last step, I would say, drying, and of course we also have lyophilization where we are again removing moisture but in the opposite direction, that means we are using lower temperature there. So we use drying because we want to prevent deamidation or oxidation of the desired product. Sometimes if you have moisture the product may aggregate or even precipitate, so we would like to dry your product actually. And also if you have a solid material which you give it to your customer, it may be easy for them to formulate because they can exactly weigh the material and then use it in their formulations. So it is more of a convenience, and especially in a pharmaceutical drug or tablet manufacture they would like your product to be in the solid form, and of course it also reduces the volume as I said before. And sometimes you may like to remove unwanted volatile materials. There could be a very small amount of solvents present which you do not want it to be carried over because when you transport a solid material with some amount of solvent, then during the transportation as well as during the storage the solvent may evaporate and the vapor pressure will be generated by this solvent. And also it is more economical and convenient to store them in a dry form rather than in a frozen form. And then drying also acts as a sterilization, that means it kills whatever bacteria or microorganisms present. And then if you have very expensive organic solvents which you have used in the previous step for purification or crystallization, then you may be able to recover those expensive organic solvents by doing drying. So these are many reasons why generally we adopt drying. But then one important point we need to keep in mind is the stability of the material at higher temperature, especially if it is a biological product like a protein. So we have to be very careful that you do not exceed their stable temperature limits. There are different types of dryers. We call it the vacuum shelf dryer or this oven dryer. You must have seen it at your house as well, where we have drying carried out in a small oven, or even in small laboratory if you have flasks or bottles or plasticware, you have washed them and then you want to remove the moisture, then we do it in a oven type of dryer, or it is also called tray dryer, so many different names. It is a batch operation, so you pack your material in the trays and keep it inside, you apply vacuum or you do not apply vacuum depending upon the setup, and then you raise the temperature, maintain it for a long period of time depending upon your protocol. So the temperature also depends upon the type of solvent you want to remove, how long or how low the moisture content has to be, and so on actually. The another type of dryer is the rotary vacuum dryer. So as the name implies, there is a rotary drum which goes round and round, and there is a vacuum applied, the drying, and then a heat is also applied. So the vacuum and the heat removes whatever moisture present and then it dries the product. The other type is the freeze dryer, that means you are applying very low temperature, so the water becomes ice, that is how it is removed, the solid ice is removed, that is called freeze drying. and then finally the spray dryers, like how you make your instant coffee. So you pass the slurry, heat it up, pass it through a nozzle, and when it comes out as a spray, the solvent completely evaporates and you form beautiful small sized fine particles, and these particles are not hygroscopic, they are far apart. So the flowability is good, appeal is very good, and solubility also increases because you have a very high surface area per volume, unlike a agglomeration or a precipitation product. Hot air dryers is basically the material is dried because hot air is flowing past it. Okay. So the hot air is in contact with the solid which needs to be dried. So the heat transfer is through convection, so it is only convection. So there are many types of dryers, like your cement kilns, cabinet dryers, tray or compartment dryers, tunnel dryers, conveyor dryers, bin dryers, fluidized bed dryers, pneumatic dryers, rotary dryers, spray dryers. All these are based on the concept of hot air coming in contact with the solid, so it carries the moisture away. So there is no direct contact between the solid and the heating element, so it is only convection. So convection means the factors like the flow rate, the factors like the turbulence that is creating, factors like a difference in temperature, all these govern the rate of heat removal. Let us look at vacuum shelf dryer, or it is also called a tray dryer. So you have a shelf and you have many trays inside. This shelf could be a cubicle or a cylindrical chamber. It is maintained in tight condition because you are applying a vacuum. Then you have heating, and there is a vacuum source, and then of course you need a condenser if you want to collect whatever solvent or moisture that is evaporating. So this is useful for drying pharmaceutical products, even temperature sensitive products is very good, and we can use it for oxidizable material because you are applying vacuum, there is no air inside, so there is no oxidation taking place. So we can do it in small batches also. So you have a few trays, you just fill up the trays with the material that needs to be dried, run it for sufficient period of time, and then you discharge all the material, then again you charge. So it is very useful for small batches and also high cost products also, because you have complete control on the drying process. So this is a typical schematic of air tray dryer. Okay. So hot air is coming from the bottom. So how do you heat the air? There could be an external heater, electrical, or it could be hot water heating up the air, and there could be a dehumidifier. So this air comes in contact with the solid material which are placed, the solid material which is placed on trays. So they travel through the porous solid material, thereby carrying the moisture as well as drying the material, and then it is finally vented out on the other side. You can have a condenser here and condense all the moisture or solvent that is present in the solid material. Okay. This is called a hot air oven. So this is a batch operation. So you need to, once it is dried, remove all the trays, remove all the solid material, again repack with the wet solid, and again you start the process. So it is a batch operation. The loading and unloading can take up quite a lot of time. Then you have the direct contact drying. That means the material which needs to be dried is in direct contact with the heated surface. So the heat transfer is through conduction. So the temperature is very high, the rate of drying is also very high, like drum dryer. So you have a drum rotating, the hot drum, the solid, wet solid comes in contact with it, it gets dried, and the solid falls away from the surface of the drum. So the surface again is clean to take up more wet. Roller dryers, belt dryers, band dryers, all these come under that category. The solid is in direct contact with the heated surface. So the conduction process takes care of two things. One is to raise the temperature of the solid to required value and also provide the latent heat of vaporization of the liquid, that means solvent or water present in the solid entrapped. One thing here you have to be careful is once the drying has happened, still the solid is in contact with the heated surface, so the material should not get charred or overheated, and in such a situation you may have denaturization, deactivation of the product, or you may have a tar formation. So the material loses its activity and also its texture and appearance. So direct contact dryings temperatures are very high, you have to be very careful about heat damage to sensitive food materials. So you can also carry it under low pressure so that you do not have to apply very high temperatures actually. You have the rotary vacuum dryer. So you have a drum rotating, there is a vacuum applied inside, the drum surface is maintained at high temperature. So the wet feed is charged as a batch and it is subjected to indirect heating, and it is undergoing agitation due to the action of the paddle mixing. So here you can carry out the operation in vacuum, we can recover the solvent by condensing the vapors as it gets generated actually. So this dryer is very common. If you go to a pharmaceutical company you may find this type of dryers. It is very good for granular pasty wet materials, it is very good for low temperature operation, it is very good for solvent recovery, we can do it in batch, it is also very high energy efficient. The mode of heating can be indirect or it can be even direct. So we can heat directly the drum surface, that way it becomes a conduction. If the drum surface is heated by some hot air that is flowing inside, then it could be a convection, and this can be, whole thing can be maintained in a closed environment. So if the solids are very temperature sensitive and air sensitive, then this is a very good operation. So it is used quite a lot in pharmaceutical, organic chemicals, insecticides, pesticides, for pasty material, dye stuffs, dye intermediates, also for solvent recovery and so on actually. So this type of dryers, rotary vacuum dryers are very common in all these industries. Freeze dryer. Now the previous dryers where you are applying heat or temperature to raise the temperature of the solid and the vapor, whereas here you are using the freezing concept, that means you are reducing the temperature so that the moisture becomes ice. So water is removed after it has been frozen. It is very good for heat labile materials like proteins, antibiotics, vitamins, blood plasma, hormones, tissue, microorganisms. So here if you raise the temperature, what will happen? The material will totally get deactivated. So there is no other way other than using a freeze drying here. So here what you do is you reduce the temperature so that the water becomes ice, so it is like a frozen. Then you have the spray dryer. By doing spray drying you are producing a dry powder, completely non-hygroscopic, so you are producing from a slurry by rapidly drying with a hot gas. It is very good for thermally sensitive materials, food products, pharmaceutical products. So here air is the drying medium. We can use nitrogen if you think the oxygen present in the air can lead to flammability or oxidation and so on actually. So if your solid contains even flammable solvent, then oxygen free nitrogen may be used as the heating medium for this material. So spray drying is nowadays used in preparation of milk powder, coffee, tea, even egg, spray dried eggs, cereals, spices, flavorings, all these are made in spray dryers. Even pharmaceutical products like antibiotics, medical ingredients, additives, paint pigments, ceramic material, catalyst support. So all these are made by this concept of spray drying. So how does it look like? So this is a typical setup of a spray dryer. So you are feeding your slurry from the top, it comes out through the nozzle as a fine spray, we have hot air coming in contact, so your solvent or water gets evaporated. So fine micron sized particles are formed here which are collected here. Now the hot air has become slightly colder because it has given the heat here, plus the moisture that was present in the solid got transferred, that is why it has become a cold moist air here. So this we can do it continuously, you can continuously feed, continuously send hot air and continuously remove the solid product. So this is a very good technique and it is widely used in food and flavoring industry. So the beauty of it is finer the particles, higher will be the surface area per unit volume. So higher is the surface area per unit volume, what happens, the heat transfer is good, so drying takes place very fast, and also if you have this as a product, a solubility also increases because it has got very high surface area to volume. For example, if I atomize it to 100 micron droplet size, the area per pound will be 50,400 feet square per pound, whereas if I bring it down, that means I make the particle smaller 20 microns, look here you are almost getting 77,000 foot square per pound of, that means you are raising it by almost a factor of 5, okay. So that is the main advantage of increasing the surface area or reducing the size of these particles. So what are the important parameters one need to consider in a spray drying? Evaporation rate, that means how fast the solvent or moisture is evaporating, because that determines the amount of air needed, how much air I need to put in to evaporate so many grams of water per minute. So that tells me how much air is required. So when I know how much air is required, that determines the size and cost of all the components, because I need to have a blower, air blower or a air compressor to match that particular capacity. So that determines the size and the cost. That is, so the evaporation rate is a very important parameter. What is the other one? Particle size distribution of the product, okay. So do I need very fine particle, do I need very large particle, should the particle sizes should be spread out or should it be very small. So that determines the atomization, so that also tells the size of the dryer, okay. So what should be my atomizer design and what should be the size. So these are the two important parameters, the evaporation rate, that means how fast you want the air to evaporate, sorry, how fast you want the solvent to evaporate, other one is what should be my particle size and its distribution, that is the product. So for a given evaporation rate, so if I fix my evaporation rate saying that I want to evaporate so many grams of water per minute, so if I have a very high temperature difference, then I will require less air. So if I require less air, then my blower can be smaller, so the whole system can be smaller, so cost comes down, okay. But then the point is I need to have high temperature driving force, that means the air has to be heated up to a very high temperature. So one of the problem may be the material which I am trying to dry might be temperature labile, that means it may lose its activity if you heat it up too much. So I can try to dry it with the high temperature driving force because my setup can be smaller, but I have to be very careful that the material does not get deactivated because of the high temperature. So you need to keep that particular point in mind. So if I reduce the temperature difference, that means I do not use very hot air but I use medium hot air, then I will require more air, that means my size of the dryer has to be bigger, my size of the blower or compressor which is pumping in the air also has to be bigger. But then the advantage is I am not heating it up to very high temperature, that means there is no worry about deactivation of the material because of high temperature. So I can reach a very short drying time and low product temperature using this type of dryer. So generally the particle sizes will be 10 to 200 microns. So I get quite a good surface area per unit volume of the material. So we can use it for skim and whole milk powders, waste solids, ice cream mix, butter, cheese, milk based baby foods, coffee, tea, dried powdered eggs. So lot of food flavoring type of applications, as I said before. And we can even dry material if it is a non-hygroscopic, that is material if it does not take in moisture on its own, then we can bring down the amount of moisture present to almost 0 value. Now most of the biological products are hygroscopic, so there will always be some residual moisture content, whereas some of the organic molecules can be non-hygroscopic, but the biological molecules are hygroscopic. So there will be some residual moisture even after complete drying. That depends on the relative humidity of the air which we are using. Now the hygroscopic material may have two types of waters, one is called the bound water, other is called the unbound water. Okay. Unbound water is the water which is present in the material due to surface tension, whereas bound water is water which is present inside the capillaries of the solid. So it will be very difficult for you to remove bound water, whereas unbound water can be removed easily. So you have a solid and it has got certain amount of moisture, and you have air at certain relative humidity. So when we bring them all together, both of them, there is an equilibrium that is formed. So the water vapor may evaporate if the relative humidity of the air surrounding it is low, or the water vapor may condense on the solid if the relative humidity of the air is high and the solid is reasonably dry, that means it does not have much moisture. So both of them come to an equilibrium, that is called an equilibrium moisture content. So you have air has some moisture, okay, that is determined by the relative humidity, and then you have the solid which has got some moisture. So when you bring both of them together, there is an equilibrium created, and the water present in the air may either get absorbed by the solid or it will get desorbed depending upon the equilibrium that is formed between the wet air and the solid, wet solid, and that is called the equilibrium moisture content. So if you look at the diagram between moisture content on the x axis and the relative percentage relative humidity on the y axis, okay. So we have something called the equilibrium moisture, and then we have something called the free moisture, okay. So as I said, you cannot dry below the equilibrium moisture for a hygroscopic material, okay. Now you also have two types of air, one is two types of moisture, one is called the unbound moisture, other one is called the bound moisture. So unbound moisture is what is the amount of moisture present in the solid. It is much more easier to remove, whereas it is much more difficult to remove bound moisture. Okay. Now the moisture content in the solid, as I mentioned, depends upon the relative humidity of the air that is surrounding that solid. So as you can see, if the relative humidity keeps coming down, the moisture content, the equilibrium moisture content in the solid also will come down. So if the relative humidity is very high, the equilibrium moisture content in the solid will also be very high. Now there are certain simple relationships which connects the humidity, relative humidity, saturation of moisture in air, okay. So you need to understand these definitions. What is humidity? Humidity is mass of water per unit mass of dry air, okay, or it could be moles of water vapor per moles of dry dry air. So if Pw is the partial pressure of water vapor, then Pw divided by P minus Pw is the humidity, agreed, where P is the total pressure. So humidity is the moles of water vapor divided by moles of dry air, okay. So this is Pw is the partial pressure of water vapor divided by P minus Pw, that gives you the humidity. Now if you bring it down, instead of moles we can use for water molecular weight is 18, and for air can bring it as 29. So this is still valid, this is the humidity. Now humidity of saturated air H naught, this is the humidity of air when it is saturated with what? Water vapor. That means at those conditions, temperature and relative humidity, this is the humidity of air when it is saturated with water vapor, completely saturated, it cannot take up any more water. Now percentage humidity is the humidity of air divided by humidity of saturated air. So obviously this is H by H naught into 100, this is called the percentage humidity. Now percentage relative humidity is the partial pressure of water vapor in air divided by vapor pressure of water at the same temperature into 100. So this is the amount of water that is present in the air, and this is the vapor pressure of water at the same temperature, that gives you the percentage relative humidity. So if the percentage relative humidity is low, that means amount of water present at that temperature in the air is low. If the percentage relative humidity is very high, nearing 100, that means it is fully saturated, lot of water is present in the air actually, okay, because it is a function of amount of water, partial pressure of water in air present and the vapor pressure of water at the same temperature. So this is percentage relative humidity. So this is a very important term which tells you how much water that is present in air and how much more the air can take up. So if the percentage relative humidity is nearing 100, so that means it will not be able to take up any more water, okay. So these are important terminologies one should know if one wants to understand the concept of dry air, wet air, bound moisture, unbound moisture and so on actually, okay. So each solid has certain equilibrium moisture content depending upon the solid properties, the porosity, what types of pores it has and so on actually. This is a picture taken from this particular reference, okay. So in this axis you have the relative humidity, that is x axis in percentage, and in the y axis you have equilibrium moisture content, that means kg per 100 kg of material. So if you take leather, the graph is going like that. So leather can take up more moisture than say wool, than wood, cotton, soap, okay. So the equilibrium, the same relative humidity, the equilibrium moisture content in leather is several times more than soap, as you can see. This is at 293 K, okay. So 293 K is 20 degrees centigrade. So if I have a graph like this for any material of my interest, I will tell at a certain relative humidity what is the minimum I can reach with respect to the moisture present in that particular solid, okay. So at a relative humidity of say for example 40%, if I take cotton, the lowest amount of moisture I can reach down to is 5 kg of moisture per 100 kg of material, understand. So the mass rate of evaporation, that means I am applying a heat, so the water gets evaporated. So here the mass rate of evaporation, kg is the mass transfer coefficient, A is the area, Ps is the vapor pressure of the water, Pw is the partial pressure of water vapor in the air, U is the velocity, okay, and raised to the power 0.8. This is the mass rate of evaporation of water. So it is a function of area, that means the area exposed to the air PS is the vapor pressure of water, whereas PW is the partial pressure of water vapor in the air stream. So, PS minus PW is a driving force for water to evaporate into the air stream from the solid stream. U comes in here because there is a turbulence forces which increases the mass transfer coefficient, that means transfer of the water vapor from the solid surface to the bulk of the air. Okay. Now, as I keep drying my material, initially there is a lot of moisture present, so drying is faster, uniformly it is getting dried, but after some time the amount of moisture goes down and down. So, whatever moisture is present inside some of those interstices or capillaries has to come up to the surface and then get dried. So, your rate of drying will keep going down. So, if you look at the drying rate curve, that is x axis is time, y axis is the moisture content. So, initially you take a wet solid and leave it in an air atmosphere. So, initially we call it settling period, so some drying takes place. After that, for a long time the rate of drying is constant, that is called the constant drying rate period. Here you have so much of moisture present, so the amount of moisture present at the surface is not the limiting. So, it is the amount of heat supplied by you enough for the latent heat of vaporization. That means your heat is good enough for the water from the liquid state to go into the gaseous state, only that is controlling. So, the rate of drying is constant. So, this is like a straight line. Okay. Now, after some time all the moisture on the surface is evaporated. Now, moisture from inside has to come out and then start getting evaporated. So, here what you have is the diffusion of this moisture which is present inside is controlling. So, the rate of drying goes down. This is called the falling rate period. So, as time goes on it becomes more and more difficult because the moisture present very much inside has to diffuse through the capillaries, come out and get evaporated. Okay. So, the rate of drying becomes a curve and slowly it peters out like this. So, initially you have constant drying rate and then after some time the rate of drying keeps falling down and down. So, if you are looking at designing a dryer and if you want to calculate what should be the drying time or what will be the drying time, you have two types of time, one is the constant drying and one other is the falling rate drying. So, you have constant drying rate period and falling rate period. So, these two times need to be considered. Now, as the drying happens and happens, the material cannot give up moisture after some time, and this moisture content is called the equilibrium moisture content, which I discussed about few slides back. So, the equilibrium moisture content depends upon the percentage relative humidity. So, the equilibrium moisture content depends on percentage relative humidity as well as the type of material, how hygroscopic it is, how porous it is and so on actually. For example, I said a leather can take up more moisture, so it will have higher equilibrium moisture content than say soap. So, here you have a constant drying rate and then you have a falling drying rate and finally the moisture content settles down to the equilibrium moisture content. This is called the drying rate curve. So, the constant drying rate, surface of solid remains saturated with the liquid, there is a lot of water. So, rate is greater than the rate of evaporation from the surface. Drying takes place by the movement of water vapor from the saturated surface through a stagnant air film. So, there is a stagnant air film, so the water from the surface passes through the stagnant air film and then it gets evaporated, goes to the bulk of the air. So, here in a constant drying period the advantage is we can call the rate of drying dW by dt is equal to a constant, that is the beauty of this. Now, there are two things happening, one is the vapor is getting evaporated and then the heat is just sufficient for the water to move from the liquid to the vapor state. okay. So two things are happening, one is related to the evaporation of water, which is given by Kg, mass transfer coefficient, A is the area, Ps is your vapor pressure of water, and Pw is the partial pressure of water in the air. This is the driving force, this is the area. We can put in velocity also here if you want to consider the effect of air flow on changes in the mass transfer coefficient, okay. Now other one is the heat transfer, that means the heat you are supplying is sufficient to evaporate or convert the water from the liquid to the vapor state, or water from the liquid to the gaseous state. So there is lambda coming in, that is the latent heat of vaporization, and we have the delta T coming here, that is the temperature difference between the air and the surface, again you have the area, then here you may have the heat transfer coefficient coming into the picture, because the heat supplied and the heat of evaporation coming. So many things are happening, you have the constant rate drying, in that period the driving force for the water to evaporate from the surface to the bulk of the gas is the Ps minus Pw, and water is evaporating because you are supplying sufficient heat for converting the liquid to the gaseous state. So this is another way of talking about the constant rate and falling rate period. So if you look at free moisture and drying rate, so initially we can call these as settling down, then you have constant rate, that is why drying rate is constant. So you have a parallel line, and then you have a falling rate, two types of falling we can put here, one falling, two falling. So this region is called the constant rate, this region is called the drying rate or falling rate, this is with respect to the free moisture. Now this is the equilibrium moisture here actually, below which you cannot dry your solid. So in the first falling rate you have the surface is drying out and the drying rate falls. The second falling rate, maybe the surface is completely dry and moisture present in the interstices or even capillaries start drying out. So the plane of evaporation is slowly going inside the surface actually. So there is a zone of vaporization taking place, so it becoming difficult for the moisture present in the interstices to get evaporated. So in the falling rate period, the rate of drying is influenced by the rate of movement of moisture within the solids, and the influence of air velocity decreases actually. So the air velocity which is contributing to the drying decreases, so it is only the diffusion. So the amount of moisture removed in the falling rate may be very small, but generally the falling rates are very large. So the constant rate may be only say few minutes, but the falling rate period could be several hours as well. So we need to consider both if you are designing a dryer. Now rate of heat required depends upon the amount of water that is evaporating and also the heat of vaporization of water, okay. So the rate of heat required Q is equal to m dot lambda, lambda is the heat of vaporization, m dot is the rate of evaporation of water, that means grams of water per minute or kg of water per hour that is getting evaporated during the process. Now let us look at some simple relationships which we might have done it in our school. The amount of heat transferred during conduction, amount of heat transferred during convection, and amount of heat transferred during radiation. Now if you have a solid material which is at T1 on one end, T2 in another end, T1 is higher than T2, so the heat is moving along this direction or heat is getting transferred. If the length is L, okay, then we can say Q the rate of heat transfer, K is the thermal conductivity of the material, A is the area, T1 minus T2 is the driving force in temperature divided by L. Oh, this is a very simple equation which we have seen long time back. So the rate of heat transfer is a function of the thermal conductivity of the material, the cross sectional area of the material, and the driving force with respect to temperature, and it is inversely proportional to the distance between these two places. Okay. Now let us look at heat transfer due to convection. This is happening in hot air ovens, where there is no direct contact of the solid with the heating, but the air which is hot is transferring the heat. Okay. So here you have Q equal to U A delta T. U is the overall heat transfer coefficient between the air and the solid. It is called overall heat transfer because it is made up of several resistances. A is again the area, delta T is the driving force in temperature. That means T1 could be the temperature of the hot air, T2 could be the temperature of the solids. Okay. So the U, the overall heat transfer coefficient, it is made up of many sub parts, because if I take a setup like this, we have some hot fluid flowing outside, cold fluid flowing inside, and separated by some metal. So heat is getting transferred from the hot to the cold. Now the overall heat transfer coefficient is made up of 3 heat transfer, because there is one heat which transferring heat from the hot fluid side here, and then you have heat transferred through the solid material, and then heat transferred in the cold fluid side. So you have 3 heats, the hot side, the material, and the cold side. Okay. That is why the overall heat transfer coefficient has to consider all these 3 factors actually. So if you have heat transfer coefficient HH as the hot fluid side, HC as the cold fluid side, and then K the thermal conductivity of the material separating these two, then we have 1 divided by UA. UA is the overall heat transfer coefficient, A is the area, equal to 1 divided by AH, that is the area on the hot side, heat transfer coefficient on the hot side, plus 1 divided by AC, that is area on the cold side, HC is the heat transfer coefficient in the cold side, plus D. D is the wall thickness, K is the thermal conductivity of this material, and A is your overall contact area. Okay. Look here, this A is same as this A. Okay. Now you can have these two areas almost same, or you can have very small d. So many possibilities are there depending upon the geometry of the heat transfer that is taking place. Okay. So if the diameter of the tube is very small, we can neglect this term. Or we can have the same H and AC, especially if you are talking about plate type heat exchangers, where you have plates, hot fluid flowing, cold fluid flowing on other side, then AH is equal to AC. Whereas if you have a tubular concentric tubes where hot fluid may be flowing outside a tube, cold fluid may be flowing inside the tube, then AH is not same as AC. But then if you have a very small diameter, if you have very small thickness material, you may be able to neglect this, and if the thickness again is very small, AH can be equal to AC, but then normally AH will be different from AC in a tubular type of heat exchanger designs, whereas AH is equal to AC if you have plate type of heat exchangers. Let us look at this continuous sterilizer. So you are having a fluid coming in, and then it gets heated up, and then finally going out. Here you may be having heat, here you may be cooling. So you have rapid heating and rapid cooling. So the advantage is, by rapid heating we are able to sterilize the material, that means you are killing all the bacteria. By rapid cooling, what are you doing is you are bringing the temperature down so fast that the material does not get deactivated. Especially it is very good for biological products which are thermally labile. So this is called a rapid heating, rapid cooling system, where one side you have the heating zone, another side you have the cooling zone, and the fluid comes in through the tubes, quickly gets heated up, and it gets quickly condensed, it gets quickly cooled. So let us look at these thermal conductivities of some material. For example, if you take polypropylene, it is 0.12 watts per meter per Kelvin, whereas if you take stainless steel it is 21, that is a big jump. Stainless steel of course is a metal, so it has got a very high heat thermal conductivity. If you take aluminium, it is again very high. So this is the best if you want to conduct, but then nobody uses this type of thing, and polypropylene is the worst because the heat conductivities are so low that it offers considerable resistance. Now let us look at the heat transfer coefficient for air. It is about 10 to 100 watt per meter square per Kelvin, whereas if you go to water, look at it, it is a big jump. So water is high heat transfer coefficient than air. So many liquids, most of the liquids have much higher heat transfer coefficient than air. Air is a very poor heating medium, but then that is how it is. So if the heating is done by hot air, the heat transfer coefficient in the hot fluid side will be much less than that on the cold fluid side, because the hot fluid side has air, cold fluid side may be having water or any liquid which has got a higher heat transfer coefficient, whereas air is the worst heating medium, it has got very low heat transfer coefficient. So if you have fluids of viscosity close to water, so when you are using such a fluid at turbulent condition, you can use this type of relationship for calculating heat transfer coefficient. Okay. So H dt is the dimension divided by K is the thermal conductivity of the fluid equal to 0.023. This is called Reynolds number, this is called Prandtl number. Okay. Prandtl number is Cp m by K. Okay. Cp is the specific heat and the m the viscosity of the fluid, K is the thermal conductivity of the fluid. Okay. Whereas the Re, the Reynolds number, it is given by dimension d, u is the velocity, rho is the density of the fluid, mu is the viscosity of the fluid. So that is called the Reynolds number. So there are many correlations available in literature which gives you an idea about the heat transfer coefficient depending upon the physical properties of the fluid. Prandtl number gives you an idea about the physical properties of the fluid, and Reynolds number gives you an idea about the velocity. So based on those you can calculate the heat transfer coefficient. So using these correlations, if you are using it in your system, we can calculate the heat transfer coefficient. So there are many correlations available for convective heat transfer for many systems. This particular reference gives you those correlations. So if you want to look at forced convection flow inside a circular tube, forced convection turbulent flow inside concentric annual ducts, forced convection turbulent flow inside non-circular ducts, forced convection flow across single circular cylinders, tube bundles, flat plates, condensation. So for different types of scenarios, for different types of fluids, for different types of shapes of the material, this particular reference gives you some correlation. So we can use depending upon the geometry and the type of system we are studying, we can get the heat transfer coefficient. So why do we need the heat transfer coefficient? Using that we can calculate what is the heat required to vaporize a liquid from the liquid state to the gaseous state. Okay. So in order to do that we need to calculate the heat transfer coefficient. The third one is the heat because of radiation. It is given by the Stefan-Boltzmann's law. Q, that is the heat transfer per unit time, is a function of constant sigma. Area T is the absolute temperature raised to the power 4. Generally in a biological system we do not use radiation type of energy for heating of a material. So and this equation is not really applicable for our studies. Conduction, yes, if you are using belt dryers, convection, yes, if you are using ovens, hot air ovens and so on actually. So once again if you look at this picture of a rate of drying on the y axis, moisture content on the x axis. So you have a constant rate drying, that is rate of drying is constant, so you have a straight line like this, then it keeps falling. This is the falling rate period, this is the constant rate period. This is called the critical moisture content, that means the moisture content which divides the constant and the falling rate period, and then finally you reach the equilibrium moisture content. Okay. So this is a typical figure which describes the drying process, the critical moisture content and the equilibrium moisture content. Now based on that, and also we said that there are two types of regions, one is the constant rate drying and falling rate drying. We have a mathematical relation which relates the drying time T to many other parameters. So T is made up of the weight of the material that needs to be dried, A is the area of the surface area, Rm is the maximum rate of drying, Xi is the initial moisture content, Xc is the critical moisture content, Xf is the final or the equilibrium moisture content. Okay. So this term corresponds to the constant rate, this term corresponds to the falling rate. So if I know what is the critical moisture and the final or equilibrium moisture content of the solid, and if I know what is the initial moisture content of the solid, if I know the mass of the solid as well as area, I can calculate what is the time required to dry that material, starting from Xi going down to Xf. Xi is the initial, Xf is the final, and the critical moisture comes in between actually. So these equations are very useful to calculate the amount of time required for drying. So today we talked about drying, the most important downstream for bringing the moisture level to very low value, and it has got lot of advantages. You can use conduction type of drying, we can use convection type of drying. Generally we do not use radiation in biological systems. Then there is something called the equilibrium moisture content or the final moisture content, below which you cannot dry a material. So there are many equations which are available which can help you to calculate the entire drying process. So in the next class we will still talk more about the drying phenomena.